Hello, my name is Uchan Kim, and I'm currently a master's student at PRM Lab Korea University. I'll begin my presentation now. I choose tour handling dynamic human voices toward singing techniques classification by Junsung Choi as my final project. The objective of this project are to classify various vocal techniques directly from raw waveform data and to effectively handle dynamic and sparse singing techniques datasets. I choose this project because my research focus is on classification tasks. I'm working on enhancing the efficiency of large language models by connecting models that match the complexity of queries. Since it is essential to accurately and swiftly perform classification based on the complexity of queries, this project aligns perfectly with my research goals. This study involves performing classification tasks on complex singing voice data that encompasses a wide range of pitches, timbres, and styles. Additionally, the research includes modeling various singing techniques and styles. I selected this task because I believe that studying classification on complex singing voice data can inspire the analysis of query complexity. First, let me briefly explain the existing project. The dataset consists of total of 3,560 WAV files with a total audio ranks amounting to 10.1 hours. To create the datasets, 20 professional singers participated. There are 17 different singing techniques used, allowing for running and analysis of various vocal techniques. Additionally, the content types includes 5 categories, each based on base vocal exercises and techniques. Next, I'll explain the datasets pre-processing process. In the project, the focus on the core vocal techniques align with project goals. He selected 10 major singing techniques out of the original 17. Subsequently, he divided the data into training, validation, and test datasets for model training and evaluation. The training dataset uses data collected from 14 out of the 20 singers. The validation dataset uses data from 2 singers to evaluate the model's performance midway and adjust hyperparameters. Finally, the test dataset uses the data from the remaining 4 singers to assess the model generation performance. This data separation helps prevent the model from overfitting to training data and ensure high performance across various singer voices. To the original project code, he uses the self-supervised learning model MERT. MERT was trained on large-scale audio data without manual labels, thereby reducing the time and cost associated with labeling while effectively extracting diverse vocal patterns and authentic features from the abundant data. This enables the model to maintain high performance on new data. MERT provides 2 types of pseudo-labeling teacher models, allowing flexibility in various learning scenarios and helping the model make more refined and accurate predictions. MERT utilizes marked language modeling, which has been proven effective in MERT. This technique allows the model to predict missing information within the context, facilitating the learning of richer and more meaningful features. Additionally, MERT fine-tunes the pre-trained self-supervised learning features for specific tasks. This enables the model to achieve optimal performance across various downstream tasks and provides customized solution tailored to specific application area. MERT adapts the transformer architecture to effectively capture long-term dependency that is highly beneficial for understanding and learning complex patterns in time series or audio data. Furthermore, by using additionally layers for specific tasks, MERT can be fine-tuned and applied it to downstream tasks, making it highly adaptable and performant across diverse application domains. I execute the existing project code in order specified by GitHub repository. Datasets preparation, extract feature, fine-tuning the model, and modifying model. As a result, he achieved the validation accuracy of 0.826, validation loss of 0.502, and validation precision of 0.826. Now, I will explain the codes that I upgraded to improve the performance of original code. First, I increased the sliding window size to enhancing performance. The sliding window is a technique that divides audio and time series data into fixed size windows for processing. Each window includes the continuous segment of data, and model learns from these windows segments. In the original code, the sliding window size was set to 5 seconds. However, the shorter window size can only capture shorter features, which may not sufficiently reflect long-term patterns and the continuity of singing techniques. Therefore, to enable the model to run patterns over the broader time range and better understand the continuity and contents of singing techniques, I increased the singing window size. Next, to adaptively learn the complex pattern of the datasets, I increased the maximum number of epochs from 100 to 200. An epoch refers to one complete pass through the entire training datasets. The number of epochs is a crucial hyperparameter that determines how deeply a model can learn patterns from the datasets. For more complex datasets, the model increased the dropout percent help prevent overfitting, given that datasets and modeling involve modeling various singing techniques and styles. I increased the dropout percentage. Additionally, since the previous two updating processes, sliding window size and maximum epochs can leading to overfitting, I increased the dropout percent to counterbalance this effect. To summarize these updated processes applied for so far, first, I increased the sliding window size from 5 seconds to 10 seconds to enable the model to run patterns over the broader time range and accurately capture the continuity of singing techniques. Next, I increased the maximum number of epochs from 100 to 200 to allow the model to run complex patterns and feature thoroughly. Finally, to prevent overfitting caused by increased sliding window size and maximum epochs, I elevated the dropout percentage. Through these methods, the validation accuracy improved from 0.826 to 0.836, a 1% increase, and the validation precision also improved from 0.826 to 0.836, a 1% increases. However, the validation loss increased from 0.5 to 0.55, indicating that the model became more overfitted. I anticipate resolving this by further increasing the dropout percentage and reducing the sliding window size and maximum number of epochs. So thank you for your attention and for taking time to listen to my presentation. If you have any questions, please feel free to contact me at the provided email address. Thank you.